recap for this chapter 2, right? For this chapter, when we look at control volume analysis, we need to study these 4 things. So we already completed the conservation of mass, which is the m dot. In and out will be the same, or mass in equal to mass out. Newton's second law is where currently we are in. So it's more on the forces that contribute to the momentum. Okay, momentum. And later we'll look at law of thermodynamics and approximation. So today we try to complete or conclude the second Newton law of motion, application for the finite control volume analysis. Right, so this is what we covered. Just to recap, the important equation will be this one or this one, right? So important equation that we look for when you look at second Newton law, F equal to ma, then you convert into momentum term, mv. So we have d divided by t, integrate your v rho dv volume. This one, if you take this integration, you will get momentum. Okay, so if you dt means the rate of change of your momentum, and we're looking at linear momentum. So linear momentum, we look at 2 dimension also, control volume and control surfaces. All right, and we know that F equal to ma. So when you take the, okay, just to recap, F equal to ma. This is second Newton law, and we know that acceleration is velocity divided by time. So we know that mv is momentum. So momentum divided by time will give you forces. So that's why you see the left-hand side, the linear momentum in control volume plus linear momentum divided by linear momentum in a control surface dimension. These two give you, this one is momentum divided by time in control volume dimension. The second one also momentum divided by time, but in control surfaces dimension. So these two, momentum divided by time, will give you forces, like what you derive from the second Newton law, F equal to ma. Okay, so for this section, we always look at force, velocity, vector, rho, and dA. Now, normally, when you look at the rho normally you can take out as you follow through the tutorial question. Right. All right. Then previously we looked at this example. So if you need more explanation, you can go back to the previous lecture. Today we look at application of the equation. So if you have tutorial question number 24, you are actually seeing the same thing. So if you look at your screen on the left-hand side, you're having like a nozzle that transfer water from the top to bottom, from the top to bottom, and okay, so this actually, if you look at the explanation or the problem statement, you see that the water flow through nozzle attached at the end of the laboratory sink faucet with a flow rate of 0.6 liter per second. The nozzle inlet outlet diameter so and so, and nozzle axis is vertical. Mass of nozzle is so and so. Pressure at section 1 is so and so. So what you need to determine is the anchoring force that required to hold the nozzle in place. Means that you need to find the force, the reaction force that keep the nozzle in this place without flying away under the water pressure. Okay, the water pressure is from the top, and then you will push this cap, the front cap, this one, to below. So we need to find the force, the anchoring force, that keep the nozzle together. All right, now for section 2, or in this chapter, when you do question on a linear momentum, there's some steps that you can follow. First, you draw your CV like usual. You control volume, you draw. Okay, so if the question already give you, then you just trace the shape and put in your answer sheet. You will get 1 mark for diagram. Okay, so sometimes it will help you with the dash line, sometimes it will not. If the question do not give you the control volume lines, then you draw and then you put in your answer sheet there. Then you get marks for your effort in showing that you understand the question. Okay, so the first step is control volume. Second step is your input and output, right? Once you draw the control volume, so in this case, you see that the line is actually tracing the cap. Okay, the line is actually tracing the cap section rather than the body. Yeah, so be careful when you defining the control volume. Control volume, actually, you look at what you need to find. For example, this question asks you to find the force to hold the nozzle in place. So what you're looking at is the nozzle. So you just trace the shape of the nozzle, and then you'll get 1 mark for that. Second, label your input. Sorry for my writing. Then input and output. Or normally you can label as section 1 and section 2, or in or out. Or you can put input or output. So step 1, control volume. Second steps, label your input and output. After that, you look for reference. Okay, you look for reference. You need to know where is positive, where is negative. So in this case, your X to the left is positive. Your Z going up is positive. So it's important you look at this axis here, because later you need to determine what is your positive and negative sign. All right. So once you have your control volume, input, output, reference axis, then you look at the flow, the flow. In this case, in normal case, you will see V. However, in this case, you are seeing, actually this is a hint. When you see W, it means that is in Z direction. So again, you have 3 axes there. If velocity in X direction, you'll see U. If it's in Y, you see V. If it's in Z, then you see W. Velocity symbol. Okay, so in this case, why you use W? Because the axis give you Z direction. So be careful. These are the area where students will always forget. Or they will, when they answer, they will look at this tutorial question and then they will forget. Actually, the lecturer did change the axis. And then they will give me the answer according to this tutorial question. And the answer will snowball, they get the wrong answer. Okay, so make sure you check your reference axis before you answer. All right. So this one, it gives you W1, W2. So when it comes to test, we will not write W1, we will write velocity input 1, or velocity input. I will not give you label also. So you need to label yourself. So make sure you know how to label. So this W1 means the flow from input, from inside the string or from the vessel. Then this is W2 is coming out. Okay, so step number 5 is your velocity. Where is in, where is out, right? Velocity. So in this case, you have only one in and one out. Okay, one in and one out. Now after you label this one, you have to check yourself whether you understand or not on the positive and negative sign. So once you label section 1, which is your input, this is your output. And we already agree that when you study about mv divided by t, which is your the rate of change of momentum. So no matter whether it is in or out, no matter the direction of the v here, the linear momentum here, when it is an input, it is always negative for the rate of change of momentum in your equation. Okay, then this one output is positive. Okay, this positive negative sign normally it link up with the, okay, I lost my mouse sign. You have the control volume plus, okay, del over del t plus the integration of control surfaces equal to force. So normally the positive negative sign is this section. The positive and negative sign. So you have one input, one output. So this section, when you answer this one, will give you negative something plus your output. Okay, so this one got answer lah. Negative something plus your output. Okay, so this is all the concept before you start answering the question. All right, now with all this in place, then we can proceed to solve this question. Okay, so they highlight all the important point there. In this case is liter per second, mm, kilopascal, kilogram. So important to look for all these unit and change them accordingly. Change them accordingly. I would recommend to change them in unit SI before you proceed. Okay, now for example, liter, if the question asks you to calculate in unit SI, so the conversion for liter will be 1 meter cube will be equal to 1000 liter. Okay, then you do conversion from this equation. 1 meter cube equal to 1000 liter. Then if the question asks you to find Q, volume flow rate, which is equal to VA, velocity times area, you get volume flow rate, which is in the unit of meter cube over second. So this one, liter per second, also is a flow rate, volume flow rate. So although here do not mention any volume here, but if you see liter per second, you have to understand that liter can convert to meter cube. So meter cube over second is the volume flow rate, VA. So actually you have this parameter inside the equation already. Okay, and then the rest, like for example, this one you need to be careful when you do the calculation. All right, so especially when you deal with a pressure Pascal. Okay, so if you forget about the unit pressure, definition of pressure will be force divided by area. So what is force? Unit force is in Newton. Area is meter square. So Pascal will be equal to Newton over meter square. So you need to know what is the relationship between Pascal and this one equal to Pascal. then normally the student will sometimes they will overlook something like the mega Kelvin and all this. Sorry, mega kilo and so on. This one comes with kilo, huh? So be careful. All right, let's continue. So before we proceed, after you draft the control volume, you pull the control volume out. Okay, then you need to know the Z here. It means that just to remind that the positive direction is going up. Okay, and we have all these symbol to represent something inside your free body diagram. Okay, so I will slowly add forces to the free body diagram here. So you scratch the control volume, draw all the points that I show you just now, the steps that I show you just now. Okay, so input and output. Then you have your first forces. So just remind that currently we are at the linear momentum section where you focus on force equal to ma, but you have to change it to mv divided by t. So we are looking at forces. Even though the question gives you pressure equal to force divided by A. So you are focusing on force. So rearrange this equation, you'll get force equal to pressure times area. So be careful when you draw your free body diagram, you are looking at forces F rather than pressure. So try to convert the pressure multiplied by area, you get the force. So you have a F1 here, means the force at your inlet. Okay. So you have your inlet force and outlet force. And focus on the direction of the arrow that you draw. It will always pointing to the surfaces. Okay. Pressure always acting on the surfaces. Pressure. This is the pressure, but you need to convert pressure into forces by times the area. You need to convert the pressure into forces. So that's why you see the arrow is pointing in. The below one also pointing in. Now this also one of the areas students make mistakes. They will unconsciously draw the arrow going down because they're so used to the normal direction. So important, the pressure is always pointing to the area. Okay, once you add the forces, so P1 times A means forces acting on your inlet. P2 times area 2 means the pressure acting on the outlet. After that, you have one more forces, which is the reaction force that make the cap holding at its place. So we adding an anchoring force. So there's an anchoring force that go against the flow because we know that the flow is in this direction. So there must be a force that counter the flow, the direction of your flow. Okay, so this is your water flow or your fluid flow. So reaction force will always opposite, go against the flow. So the direction is going up, FA. Okay, so once you have all the forces, the blue color is the pressure, red color is the anchoring force. Next, in this case, you need to consider gravity because you see the G in the diagram. There's a G pointing down, means you need to consider. And the question also didn't mention that you can ignore or you can forget about gravity. The question doesn't mention that. So you need to consider the gravity force. So this is an example where you need to consider the gravitational action or effect. So with gravitational, then what is the gravitational force? Is that all the fluid, all the medium that having a mass, the gravity will have interest on it. So the mass of the water times the gravity, you get Wn. Wn, they have two gravity action here. One is the nozzle, one is the water. So you have a two green arrow here, and the arrow is pointing down because the weight is pointing down. The gravity is going down. So the first one, you see the first green color arrow here is the nozzle weight, okay, Wn. As long as all the object that having mass, then it will fall under gravity action. So you have two objects that having mass here. One is the water or your fluid, one is the nozzle. So you have two green color arrow here, Wn and Ww. W means for water. Okay. Then after that, you have one more forces there. With this, we just add in the a bit light yellow with the narrow arrow here. You have two, right? So one is W1, one is W2. So I think you're not able to see the W2 arrow. Arrow is pointing down. W2. It means that this is not weight. Small w, it means the velocity. Apologize for my writing. Velocity, so velocity at point 1 and velocity at point 2. Okay, once you have all these things, then you can start solving the question. Oops. Okay, so I put the diagram on the one side. So just to summarize, what you need to prepare before you solve for a question that you need to deal with linear momentum or second Newton law is all the force, all the forces, all the force, velocity v, gravitational force, it is mg. We give you w, weight, okay, velocity, weight, your pressure. Remember pressure, so maybe I will not put pressure here. So pressure is under forces. Okay, pressure times area give you forces. And then some reaction force, in this case is the anchoring force. So velocity in this case is going down. So you're having or in Z direction, you're having a W symbol. Weight in this case under gravitational force, you have a nozzle weight and water. Okay. So make sure you have all this information in your answer sheet there. The next is just substitution of all these parameter inside the equation. Right, the rest is just mathematics, doesn't have any complex steps there. Okay, so you write this equation, linear momentum equation, consists of what is happening in CV plus what is happening in CS equal to force. Okay, now I want you to pay attention to the structure of the equation. It will be different from the first concept, which is the m dot. It will be different. Don't mix up with conservation of mass and linear momentum. Will be different. Okay, so make sure you know to use which one is the correct equation, and it will always come up with the force on the right hand side. Okay. So after you have the equation, so you write this equation, you'll get 1 mark for this equation. Then the rest is just substitution. So the second step is that the flow must be stable inside this control volume so that there's no losses inside the system. Okay, so second step, you draw an arrow equals 0, steady. Okay, so let's look at the statement. Is there any steady here? So in this case, there's no steady flow inside there, but when it comes to exam, you will be seeing you'll be seeing the steady flow inside, or in this case, you're seeing the flow rate of 6 liter per second. So if you have a Q value in the system, it means that we also assume that we have a steady flow inside the system. Okay, so these are the explicit, implicit information, right, that you need to know. So after that, you add in this blue arrow, write steady equals 0, you get 1 to 2 marks for the understanding of the steady flow, the effect of steady flow on the control volume dimension. So then after that, you simplify the equation. You only left out this one. So you do this section first. So this one's 0 already. So you focus on this section. Okay, so this section, when you rewrite the equation or rearrange the equation, the first thing that I look in your answer will be the conversion of all the notation. Okay, what do I mean? Look at V. When you write your answer, the V you should already know to change to the direction of the velocity. Okay, this is velocity direction. And it must tally with your free body diagram. So in this case, because your Z is going up and you're looking at Z, so that's why we are using W rather than V, U, and so on. So for Z, we use W, row copy. This one is the vector dimension that we will look at. So this one will give you, depends on your inlet and outlet and all the forces that you have, okay? Later on, so the A you copy lah, okay? So we complete the left-hand side. Then you deal with forces. Then you deal with forces. So forces, you just look at your free body diagram. What is going up is positive because your Z direction is going up positive. So you look at the arrow. If you go up positive, you're going down negative. So you have positive FA, negative WN, refer to nozzle weight, negative pressure times area, negative W, W means water, plus PA, P2, A2. Okay, I'll pause for a while. Look at these slides. Any dimension here that you're not familiar or it seems confused to you?
No, sir.
Okay. Ask me a question before I ask you a question. Make sure you understand the structure of the equation here. All right. Let's move forward. So be careful why there's a negative, positive, and so on. So the next time we're going to look at this component. Okay. Again, positive is for outlet, negative for inlet. Okay, in this case, because from the diagram, the W already draw the uniform distributed symbol. What does it mean? You see all this symbol? This is well-distributed flow. Or we can say that if you see this one, it means you have a steady flow. Okay, it's also another information that you can extract from the question itself. If you see this well-distributed flow in and out, meaning you're having a steady flow. Okay. Next. Okay. The next, because we are having a water or fluid, the flow is incompressible. Okay. So remember, when you use the incompressible, it will always link with your rho, the density. Okay. The density. Okay, so I pull the equation up. The rest I will just show you. I do not touch the left hand side. The left hand is the forces. Sorry. Okay, the left hand side is the forces that we derived just now. Now you look at the right hand side. I want you to focus on the symbol. Okay. This one is your input. This one is your output. So before you start anything, the input component is negative. Output component is positive. So this is a symbol there. So your input, the flow, you look at the flow, the flow is going in, input. So everything happened in this section 1 or input will give you negative sign on this component. So if it's input, give you negative sign. If it's output, it give you positive sign. Okay, next we just process the information. So you know that rho VdA, this one, rho VA or rho AV. Any of these will give you m dot, like what you did in the mass flow rate, conservation of mass earlier, rho AV. Okay, now if you're still not able to see that this is a m dot, what you need to do is just analyze the unit of each parameter. Okay, I'm not going to go in that. So I already done the analysis for you in previous section. So if you still don't understand why rho AV or rho times velocity times area will give you m dot, go back to the previous lecture video or PowerPoint slides to look at it. Okay, so rho VdA give you m dot. And the next one I'm going to explain and slow down a little bit. For input, you look at W. You look at W. W direction is going down. Your Z direction is going up. So what you need to do in your equation, you need to add a negative sign for W. Yeah, because we are looking at a vertical direction. Okay, and this one is the string or nozzle case. It will be different if I convert or re-engineer the question into fountain. I'll give you some hints already. What happens if I give you a fountain question by using a volcano or something that the water or the fluid is going up rather than going down? Just have a thought after this. But for this tutorial question, what I highlight is the W is going down and it's opposite of your Z. So that's why we have a negative sign here. Same, I already explained the positive sign for m dot. Positive sign for the whole thing. In this case, you should understand why there's a negative sign for W2. Okay. Should understand, huh? Okay. Let me ask the Ku. Ku, are you there? Ku, are you there? Ku Yichen, are you there? Ku, are you there? Mr. Ku, are you there? Okay, I will ask the question to Raj. Raj, are you there?
Yes, sir.
Okay, Raj, look at the diagram or on your screen. Explain why there's a negative sign in front W2. Okay, yeah. You are the one who decide what time we end our session. Eh? You want to drag, I can drag, no problem. Explain why there's a negative sign.
Sir, I think because of the Z axis, it's going upwards, and then the W2 is going downwards. So
okay, correct. Excellent. All right. Just check. Huh? Cool. Are you still there? Are you still in the class?
Yes.
Okay. All right. So we're done with the explanation for how you expand this one, how you expand the forces. Okay, the rest is just rearrange the equation because what we interested in is your anchoring force. You rearrange the equation in this second equation here, right? Move your FA to left hand side and then you rearrange the equation. The rest is just substitution of all the parameter. Okay, so m dot is the same for in and out. So you can calculate. So I already explained how you get the Q already since the beginning. All right. And I already explained how to convert liter to meter cube. I already explained already. Rho of the water is 999 kilogram over meter cube. Later on, I will give you a table. You need to refer to the table according to temperature because water will change the density according to according to temperature. So for this tutorial question, we will use 999, or you can use 1000 for this tutorial question. However, when it comes to exam, there will be a table that give you a reference value for that particular temperature. Okay. Yeah. So just give you some idea what's going to happen. So if you substitute the value, you can get your m dot, which is equal or near to 0.06 or 0.599 kilogram over second. Your W will equal to 2.98 for inlet. W2 will be different because the area changes, although the Q is same. Area is different. So you get your W2 equal to 30.6 meter square. So there will be some marks for W1 and W2. Okay, so make sure you know why suddenly I can calculate W1 and W2. Okay, once you get all these value, calculate the Wn, which is the mg, because you are given the mass of the nozzle times the gravity, and already mentioned gravity for this module is 9.81 unless you're given a fixed value in the question. If not, use 9.81. For water, you know that water you're able to find with rho times volume times gravity. So how to find the volume in this cylindrical shape? You have to know lah. Okay, how to find a volume in cylindrical shape, because if you draw in 3D, you're having a cone, not cylindrical, sorry. You have a cone shape. How to find the volume? You have to go and flip your advanced mathematics or mathematics textbook. How to find the volume for this cone shape. Okay. So it's a cone volume. Huh? So I just give you some hints. So there's some equation for cone. Then you find the volume. Okay, you find the volume accordingly. At the end, you'll find your water weight equal to 0.278 Newton unit. Important, Newton. Then the rest at the end. Okay, we have done for this one. Done for this one. We have done for this one. We have done for this one. So we have a subsonic flow discharge to the atmospheric. Discharge pressure will be the atmospheric. So if we are using gauge pressure, which is here. So if any surfaces that exposed to atmospheric, your pressure in your equation will always, we will cancel out. We'll use pressure equal 0. We will use gauge pressure. Gauge pressure means if you put a sensor at this point, the sensor will show 0 in the reading. If you put a pressure sensor here, the sensor will read 0 because there's no pressure there. But if you put a gauge pressure here, there's a pressure reading in at this point because the water pressure on the gauge. Here, atmospheric pressure and the surrounding is same, so there's no reading at this point. Okay, now this is also another trick question or another area that student will forget when it comes to test or exam. So every time you have a pressure exposed to atmospheric pressure, the pressure reading at that point will be 0. So your P2 is 0. Sometimes we will just give you some hints, or we'll give you bonus mark in the question. We'll purposely ask what is the pressure reading, or what is the pressure value at the input at that particular location. For example, right? We'll ask you, for example, what is the reading at P2, or what is the reading of P2? The answer, the bonus question, is just 0. You put P2 equals 0, you get the full marks for the understanding of what is the why they means that you understand why you can put 0 there. Okay, because that area exposed to atmospheric pressure. Then you substitute all the value, you get anchoring force equal to 7.8 Newton. Okay, 7.8 Newton. What is the direction if you get positive? Okay, cool. Are you still there?
Yes.
So the answer for anchoring force is positive 7.8 Newton. So based on this calculation, what is the direction of FA? What do you think? Is it going down? Going to the side? Going up? Or going to the left? What do you think?
Going up
Why? Why is going up?
because the arrow of the FA is pointing out.
Yes, correct. And because why you pointing out? Because what do you do understand? Cool. Why the arrow pointing up earlier? Why we put going up and rather than going down? Why? Why FA not going down?
Because FA is positive.
Yeah, we know positive, but what is the reason we put the arrow pointing up? There must be a reason why it is not pointing down. You know what is FA or not?
Force, right?
Yeah, what force?
Equerry force.
What is anchoring? What do you mean by anchoring? What do you mean by anchoring? Okay, maybe you listen to Shirley explain. Shirley, are you there?
Yes, sir.
Okay, Shirley, can you explain why the FA, the anchoring force, the arrow, earlier we decide that it is pointing up and not pointing down? Why? Why not pointing down?
Because of the row 1, A1, they have a relationship there.
You mean P1, A1?
B, Finite row.
Okay. So because the pressure of the water is pushing the cap, the pressure is pushing the cap away, okay, to this direction. So the wording anchoring, it means, yeah, good actually. That the meaning of anchoring means what is the force that hold the cap to the body of the vessel? Cool, you understand or not? Cool, do you understand?
Not very.
Okay. You look at look at this question. Do you see two body here? Do you see two individual body in the diagram? This is body 1. This is body number 2. Do you see it?
Yes.
So if you press water in this direction, what will happen to the body number 2? What body number 2 will feel if you press from above? You pump water from above. What will B2 feel? Or what will B2 tends to go? What is the natural reaction if you pump water from above? What will the B2, if you're B2, where will you going? You going down or going up?
Going down.
You'll be going down, right? Okay.
Yeah.
Now the question asks you to determine the anchoring force, meaning there must be some force over here that lock the body between B1 and B2 that doesn't allow body number 2 to fly away, to move down. That's why your FA is pointing up. Do you see the logic? Cool, do you see why FA now is pointing up?
Yes.
Okay. Make sure you understand, huh?
Yeah.
Okay, good. With this, I end the recording first. Let me see, is there any slides there? Okay, yeah. So I did explain. So what happens if the nozzle is not fastened securely? So if the nozzle doesn't, if the force is less than this one, if the anchoring force is less than 77.8 Newton, what will happen? So normally there is one section, which is the last question or last section of the question when it comes to test or final exam, maybe your assignment, it will ask you to elaborate what will happen to your value. For example, in this case, the anchoring force is 77.8 Newton. What happened if the designer, for example, Koo, he designed this structure, and he put in the anchoring force is maybe 50 Newton, 50 Newton. What do you think the nozzle will happen? Right, so it will fall out because the anchoring force is not strong enough to hold it at its position. Okay, so the nozzle will be pushed off the pipe. So the nozzle will fly below, will fly away. Okay, so this is how you explain if the question asks you what happened if the question gives you a value and you need to check with your answer, you need to explain the result. What happened if the FA or the designer designed FA, the anchoring force equal to 50 Newton, what happened to the nozzle? Or if the designer designing the anchoring force at 1000 or 100 Newton, what happened to the nozzle? You need to know how to answer. Okay, so there's one particular question they will ask you to explain to test you whether you understand what you're calculating or not. Okay, since you're already third year, the reason why we design such a question because you're going to work later on. So normally there's a reason behind all your calculation. So this is where we start training you to think whether your calculation is correct or not. You can do a self-check. Okay. Okay, solution 2, I will let you to go and read from my slides. Okay, so there are two solutions there. I give you the first solution. Second solution is what happens if you have a different approach. Okay, you put in the atmospheric pressure in all your control volume, and then you see what happened. Okay, so the previous one, you look at the one that we show on the left. The second approach, you only look at the cone section. Okay, but if you look at cone section, then you need to include the atmospheric pressure. Okay, and so on. It still gives you the same answer, same results. It's only the approach will be different. Okay, so I show you just the differences of the parameter. So if you use a second approach or second solution, where your pressure is over the vessel or over the control volume, then you will see the pressure when you convert into forces, your P1 plus P atmospheric must be counted. Same with point number 2. Okay, so I stop my recording.